Hello, welcome to the lecture number 8 of the course Quantum Mechanics and Molecular Spectroscopy. As we usually do, we will take a quick recap of lecture number 7. In the lecture number 7, I told you that we start with a n-state perturbation theory, which simply means that you start with a Hamiltonian H0 and for a nth state psi n you get value E n n. This is something that you know, and your total wave function psi can be written as sum over n a n of t e to the power of minus I E n t by h bar n. And then you have a time dependent perturbation which is nothing but h prime of t, so that the total Hamiltonian will be equal to this, and then you propagate using time dependent Schrodinger equation, which is nothing but I h bar t by dt is equal of psi equals to h of psi. Now we use this to get to equation after some rearrangement and algebra, that sigma over n I h bar C n dot t e to the power of minus I E n t by h bar n equals to sigma over n, sorry, a n, we call it a n t, not c n t, a n t, a n of t e to the power of minus I E n t by h bar h prime of t acting on n. Okay. Now what we did is, after that we used multiply with psi m star on the left. So that is nothing but multiplied with m and integrate. When you do this, what you get is I h bar sum over n a n dot t e to the power of minus I E n t by h bar m n, this is equal to sum over n a n of t e to the power of minus I E n t by h bar h m h prime of t n. So that is what you get. So what we had is I h bar sigma over n a n dot t e to the power of minus I E n t by h bar m n equals to sigma over n a n of t e to the power of minus I E n t by h bar m h prime of t n. And then we argued that since form complete set, and these are solutions of H naught, they are orthogonal or orthonormal. That means Mn is equal to del Mn, that is nothing but is equal to 1 when m is equal to n and is equal to 0 when m is not equal to n. Similarly, on the right hand side we said m h prime of t n is equal to 0 if m is equal to n and not 0 or may not be equal to 0 if m is not equal to n. Okay. This is 0 if m is equal to n, because we said that you cannot look at perturbation of the state onto itself, or you cannot look at the transition from a state to itself. Okay. Therefore, these are known as self transitions, okay, transitions of a state to itself and which cannot be observed. So, we take it to be 0. So, based on this equation will turn out to be IH bar. Now, we can drop summation because the left hand side of the equation will only survive when m is equal to n or n is equal to m. In that case, you will get am dot of t e to the power of minus I em t by h bar, okay, and m dot m and this integral will go to 1, and this equal to, in the right hand side all the terms survive other than when m is equal to n. Okay. So, that means sum over n not equal to m a n of t e to the power of minus I e n t by h bar m h prime t n. Okay. So, we arrived at this equation towards the end of the last class. Now, we will continue with this equation. So, what do you have? Okay. IH bar am dot of t e to the power of minus I em t by h bar equals to a n sum over n not equal to m a n of t e to the power of minus I e n t by h bar integral m h prime of t n. Okay. Now, this is what is given. Now, we have one issue that we need to look at, okay, or we can just rearrange. First, before we look into it, let us do some rearrangement. Okay. So, IH bar, when if I want to take the other side, so this will become am dot t equals to 1 over IH bar, okay, and sigma over n not equal to m a n of t not equal to m e to the power of minus I e n t by h bar into e to the power of I e m t by h bar m h prime of t n. So, this is equal to, now if I write this 1 over IH bar sum over n not equal to m a n of t e to the power of minus I e n minus e m t by h bar, okay, m h prime of t n. Okay. Now, I can write e n minus e m, sorry, e n minus e m is equal to delta E is equal to h bar omega n m. Okay. So, if I write that this is equal to 1 over I h bar sigma n not equal to m a n of t e to the power of minus I omega n m t, because this h bar here and this h bar will get cancelled and you will get m h prime of t okay. Now this is going to be the, so this is nothing but d by d so the left hand side nothing but d by dt of am of t, because I told you am dot is nothing but its time derivative is equal to 1 over I h bar sigma over n not equal to m a n of t e to the power of minus I omega n m t m h prime t n. Okay. So, that is the integral that we have to. Okay. Now, we will see that the time dependence of a coefficient m will depend on all the other coefficients a n's where n is not equal to m. That means, if you have a3, let us take m is equal to 3 and there are total number of wave functions are 10, then time dependence of a3 will depend on a1, a2, a4, a5, a6, a7, a8, a9, a10. Okay. So, it will depend on the time dependence of all the other rest of the coefficients. So, what we have is d by dt of am of t is equal to I h bar 1 over sigma over n a n of t e to the power of minus I omega n m t m h prime of t n. Okay. Now, I just want to find out am of t. So, am of t will be equal to 1 over I h bar integral of sum over n a n of t e to the power of minus I omega n m t integral m h prime t n dt. Okay. So, that is the integrated form of this coefficient and this is the most important. Okay. Now, to get to this equation I have not made any approximations because all the math that we did was completely rigorous. No approximation was made to get to this equation. Okay. Now, unfortunately, this equation involves coupled differential equations of n coupled differential equations. Okay. So, if there are total n coefficients, each coefficient mth coefficient will depend on rest of all the coefficients. So, you will get a series of coupled differential equations. Totally, if you have 10 such coefficients or 10 such wave functions, then you will get 10 coupled differential equations. Okay. If you have 20 of them, then you will get 20 different coupled differential equations which are going to be very difficult to solve. Okay. So, then at this point of time let us make a small approximation, and that approximation I will call it as first order approximation. Okay. What do I do in the first order approximation? Okay. To begin with, when there was no perturbation, what did we have? When there was no perturbation, then we had H naught of n is equal to En n. Okay. Now let us suppose there is a initial state I. Okay. So which means H naught of I equals to Ei I. Okay. What is this initial state I? Let us state this initial state as a ground state, or we can say this is H naught of ground state G is equal to E of ground state into ground state. Okay. Now if we had a ground state, all the population would be in the ground state, and all the excited states will not be having any population. That means at t equals to 0, without perturbation, only the initial state was populated. That means Ci of 0 equals to 1, and this will correspond to state H naught I is equal to Ei I, and C of any other state, let us say F, okay, of 0 is equal to 0, and this will correspond to H naught of F is equal to EF of F, where F is not equal to I, okay, is 0. That is the initial. So only the ground state is populated, or only the initial state is populated. I could set initial as ground. Okay. So Ci of 0 is equal to 1 and Cf of 0 is equal to 0. Okay. Of course, F here means all the other states other than the Grignard state. So if let us say quantum number 1 is I, initial state is quantum number 1, then H1 or C1 is 1 and C2, C3, C4, C5 etc. are zeros. Okay. If with energy E1, as in the case of harmonic oscillator. In the case of harmonic oscillator, 0 state is populated, as in the case of particle in a box, only n is equal to 1 state is populated. Okay. Now and anything other than 1, that means states 2, 3, 4 etc., they are not populated. Okay. So that is the scenario when you when you do not have the perturbation or without the perturbation. Now what you want to do is that let us consider a weak perturbation limit. Now what does weak perturbation limit says? If you have a weak perturbation limit, we will assume that under such limit, thus even when you switch on the perturbation, the coefficients do not change too much. Okay. So weak perturbations, what happens is that the coefficients do not change. Okay, this is the approximation that I am using. So we are using a weak perturbation limit, and then we are saying that the coefficients do not change. That means Ci of t will still be equal to 1 and Cf of t will be equal to 0 for f not equal to I. Okay. Now let us go back to our initial equation. What was that? I said Cm of t equals to 1 over IH bar integral, okay, sum over n, sorry, an, not C, an of t e to the power of minus I omega nm of t m h bar t. Okay. Now what I am going to say? So AI is equal to AI of t is equal to 1 and AF of t is equal to 0, okay, as long as or an of t is equal to 0 if n is not equal to I. In such scenario I am not, then I can write AF of t, that is what you want to evaluate, is equal to 1 over IH bar integral of, all of them will go to 0 because the coefficients will 0, only one coefficient will survive, that will be AI of t, okay, e to the power of minus I omega Fi t m h prime of t dt, okay. A of t, this is equal to 1, so mul has no meaning in multiplying, so we will get AF of t is equal to 1 over IH bar integral, of course we have to integrate over some time t prime, e to the power of minus I omega Fi t, and this will become f h prime, okay, this will become f and this will become I of t I t t. Okay, so that is my coefficient of f state, and if I want to consider the probability of f state P of f of t, then I will take modulus of AF of t whole square. So this will become 1 over h bar square integral 0 to t e to the power of minus I omega Fi t f h prime of t I t t whole square. Okay. So this is the probability of finding the fth wave function. So that allows the transition from I state to the f state and the probability of such transition. So we will stop it here.